So hello, welcome to 229. So we're starting a block of 3 lectures that I get the privilege of spending some time with you and kind of walking you through the building blocks and basics. Before I get into the plan for those 3 lectures, I want to make sure we understand a couple of logistics. So I posted something on Ed that kind of explained why I was setting up lecture in the way I am. You are not obligated to read that, but if you're interested, go ahead and read it. Super happy to take feedback and discuss any of that. One of the things that I liked about the pandemic was that more people were asking questions during class, and I think part of that was because people were using the anonymous feature on Zoom quite a bit, and I wish we still had that. We don't in this class for various reasons. So what we're going to do instead is we're going to have this Ed thread that I just set up that says Lecture 2 330 in-class question thread, and feel free to fire away questions on there. I may not take all of them. I reserve the right to skip them. TAs may jump in and answer some, and I'll try to follow up on anything that's there. But it's really helpful to me that you ask questions, and happy to talk about whatever you want, really. Maybe relevant to the class is helpful, but like pretty much whatever you want. Second thing, there are a couple of downloads that I put up before my lectures. I put up 2 things. One is a handwritten note of what I'm going to talk about, which are the same notes that I use. I modify them a little bit. And then also a template in case you want to follow along. Again, you don't need any of this stuff. You can just sit, watch it on video, watch it here, ask questions, do whatever you want. But it's just so that you know the material that's there and that things like data that I want to show you and look real, I can cut and paste that in and you can have it in front of you while I go through it. Okay? All right, so that's the logistics. I'm going to try and use the iPad. I like using the whiteboard feel. So this is a good compromise because it slows me down. If I get excited, I'll start talking all kinds of nonsense. So this will focus me a little bit more on the class, and you'll see how long I last. All right, so what we're going to do in this first 3 sections of the class, first 3 lectures, is kind of build up increasingly sophisticated machine learning models. And what you're going to see is that they're very, very similar to a model that you probably already know and love, which is linear regression. If you don't know linear regression, don't worry. Today's lecture is effectively going to be talking about linear regression with slightly fancier notation and some little bits around the algorithm, but it's basically just fitting a line. Okay? It's really hopefully going to be something that you've seen and you can grab onto. And then what we'll do in the next lecture is we'll generalize this from regression, which is the kind of traditional fitting a line, to classification. And that'll have a couple of twists. We choose our notation a little bit carefully, and what that allows us to do is show that way that we're looking at classification, and we'll talk about what classification really is, allows us to do a much larger class of models, which are called these exponential family of models. And they're going to kind of rear their head throughout the course. So we're going to see a precise definition that allows us to have a huge number of statistical models and kind of treat them in one way. So we don't have to understand the details of every little model. We have an abstraction of how to find its parameters, how to do inference on it, let's get a prediction out of it, and kind of understand it, and kind of understand these algorithms. I'll try to highlight for you as we go through there which of these pieces actually carry over to what I would call kind of modern and industrial machine learning. Feel free to ask questions. Effectively, the way we solve these algorithms or what we solve these underlying optimization problems is exactly the way we run everything from how images are detected to how search works in various different corners of it to natural language processing to translation. Weirdly enough, this abstraction kind of carries over for all of that. And the underlying workhorse algorithm, which we'll see, is called stochastic gradient descent. And so we'll try and introduce it in that absolutely simplest setting. Okay? And so that's the idea. It's going to be building parallel structure for the next kind of 3. So linear regression, classification, and then we're going to go through this generalized exponential family. And they will have a very parallel structure. If you go back to the notes, you'll be able to pull out like, oh, this is the solving part, this is the model part, and what we're going to do there. All right, then Tengyu takes over, teaches you a bunch of awesome stuff, neural nets, all the rest of that stuff, kernels. Then I come back and teach you unsupervised, and there again is a different structure there, but it's very, very similar. And graphical models and the rest make an appearance there. Okay, so today our plan is to get through first just some very basic definitions. We'll be a little bit pedantic there, but that doesn't mean you shouldn't ask questions. It means if you don't understand something, you should, and I haven't done my job, so just fire off a question in any form you like. Then we're going to talk about linear regression, which as I said is fitting a line, except we'll be fitting high dimensional lines eventually, so we're going to want to abstract that away. We'll talk about batch and stochastic gradient descent, which are 2 algorithms. In machine learning, as Tengyu talked about, we're not great with terminology. This algorithm was called incremental gradient descent in the 60s. It's been around forever. Or incremental gradient methods, actually. It's not even a descent method formally. Doesn't matter. The point is these are old things that people have been using for a long time, and weirdly enough, it's what we use every day. Like it's, as I said, this is like a workhorse algorithm that you're going to see. And then I'll very briefly cover the normal equation because I think it's occurs on your homeworks. And it's like, also gives you some practice with vector derivatives. So you do need to know the vector derivatives stuff to make your life easier in this class. You'll have to occasionally compute a gradient or compute a derivative. And this is a place where you kind of know what the right answer is. So when you compute these derivatives, it's an easy place to check yourself. But I wouldn't say that normal equations are the most important thing you'll learn in this class. It's just, solid. You should know what they are. I mean, it's not hard. Okay. All right, great. So let's talk about supervised learning. All right, so this next section, as I mentioned, is going to be all supervised learning, and it'll all follow kind of the same general schema. Right? And what I mean is, we're going to try and have some, what we call prediction function. And basically all that's going to be is a function h, which we'll use this notation consistently, that goes from some set x to some set y. Okay? Before defining this formally, let me just give you a couple of examples. So one idea is that x could be some set of images. Right? So we could look at a bunch of images, and we could ask, does it contain a cat? Right? That was actually a very important machine learning problem at kind of one point in time. People still work on that. Right? What's the object that's in this image? That would be a prediction. Right? Your y's here would be a set of labels that say things like cat, dog, things like that. Right? It could also be text. Right? So we could look at text here, and we could ask questions that maybe we arguably should do better on in machine learning, like, is it hate speech? Right? And so we ask here, this x here, these are all examples of data types that we want to work on, and these are all labels or y's that we're talking about. Okay? Now we'll look at, as Tengyu showed in his lecture, we'll look at house data. Now, historically, house data has been one of the most common machine learning and statistical tasks. It's in every Stats 101 course, so you may have seen this before. I kind of hoped you have. And when we look through it, I'm gonna point out the real data that you can use to try this out in a competition like Kaggle. There's a Kaggle where you can download house prices from Ames, Iowa, and try and guess how much they should sell for, things like that. Right? People actually make money on that, by the way, right? Not everybody, sometimes hard if you followed the news, right? Zillow tried to sell houses and estimate them and flip them, and they lost a bunch of money. Blackstone, if you care about private equity, managed to make money doing that, right? They bought houses and they were able to predict how much they were going to sell them at. So as maybe trivial as this seems, these are actually problems that people care about. Okay, anyway, so we need an abstraction. So we have this x and we have this y. We need something else to make this a supervised problem, and we talked about it yesterday. We're given a training set, okay? So what is a training set? Well, formally, it's just going to be a set of pairs. This is just introducing notation. You have an x1 and a y1, okay? Now, comma, all the way, xn to yn. All right. All right. Now, xi here is going to live in x. It's some encoding of an image. Maybe it's the bits that are in the image. That would be a reasonable encoding. Maybe it's the RGB values that's in there. If it's text, maybe it's the ASCII characters or Unicode characters that are in there. It's some bag of bits, okay? Now we're later going to abstract this away and almost always work in a vector space. And we'll talk about where those vector spaces come from. But that's kind of where the data actually lives. And yi is going to live in some set, and those are going to be our labels. Oops. All right. Okay. All right, so now our do, given that information, is we have to find a good h, x to y, okay? And often we call it h because it's a hypothesis, all right? All right, now, that notion of good is going to occupy a fair amount of what we worry about over the next couple of lectures. What does it mean to be good, right? In some intuitive sense, because I have these examples of x's and y's, one reasonable thing I should expect is I kind of get them more often right than random chance, right? That's kind of a very basic idea of what would be good. You show me an image, it has a cat in it, I get most of the cats right. Now you've used enough machine learning to know we don't get it right all the time, right? And it's still useful. So we'll have statistical notions. We'll try to get it right kind of on average. Now, more advanced things like just recency bias, because Tatsu was talking about it in the class before on the board, you could also worry about how well you do on some groups versus other groups. Some groups, you're predicting really well on, but other groups have qualities and you're not predicting as well on them. You could worry about that and say, I want to do, my prediction I only care about is being, as well as I do on any one of these predefined groups. Okay? So you could have multiple notions of good. We're going to stick with the simplest and basic, which is like, how accurate am I at the task in this? Okay? But this mathematical framework can accommodate all of those. Like when you actually write it down, the tweaks that I just mentioned to come up with those different, what they're called loss functions, is really, really kind of straightforward mathematically. They'll kind of go through the same thing. Okay? So all I want you to take away from this is we have a training set. That's what's provided to us. These yi's are going to be supervision. They're in some set. Our goal will be to find a good h among all the possible functions. And by the way, the class of functions from like one space to another is enormous, right? So we're going to have to restrict that in some way. And that's kind of the setup for supervised learning. Okay? All right? Now, this here we will often refer to as the training set or the training data that's there. And what we're really interested, by the way, in, which is probably a little bit counterintuitive the first time you hear it, is we're not doing strictly, machine learners are not doing strictly what's called interpolation. We're not just trying to predict back on the x and y pairs that we have. We're going to try and worry about how well we're going to do on a new x and a new y. So why does that make sense? Imagine someone shows up with an image. Odds of that, like, they just took it with their phone, right? My phone is just littered with pictures of my daughters, okay? So if I take a new picture of my daughter, probably the label should be the same as the last 1,000 pictures I took, but it's going to look a little different, right? So when I show that picture, I don't care how well I did on the last picture that I took of her, I care how well I did on this picture, right? On those x and y pairs. And that's a little bit weird. And that means that implicitly what we're going to assume here is that these x's and y's you should think about is drawn from a large population of images, right, that are out there. And we want to do we're sampling some piece of them, and we want to do well on those images that are going to come in the future. That's why we think about it as a prediction. So it may not be great to just return the label of every x and y we've ever seen, right? We have to in some way kind of generalize, is the technical term, to those new images. Okay? All right? So the reason we call this a prediction is we care about new x's that are not in our training set. All right? Now, if you look at that and you're mathematically minded, you're like, how the heck did you say anything about that? And hopefully you got a clue there. If it doesn't make sense yet, don't worry. We're going to make some assumption like we randomly sampled from all of the images, and how well do I do on another randomly chosen image? Okay? That's what we're going to do. In some way, the set you train on, though, better be like the set that you evaluate on, that you take your predictions on, or you're out of luck. If you train your model on pictures of my daughter and ask to know about cars, I don't know how well it's going to do. Right? So there's clearly some link here. Now, weirdly enough, although I say that, one of the big trends in machine learning that's going on right now, and in fact, the course that I co-taught with Tatsu and Percy last quarter, was about these large models that we just trained to predict kind of everything that's on the web, and they seem to do pretty well on things. Okay? So just want to highlight, like, there's a really strange notion of good. You spend your whole life trying to think what good is, if you're a machine learner. Okay, a couple more things. As I said, I'm just going to go off on tangents if no one stops me. All right, so if y is discrete, this is just terminology. So it's a discrete space. We think about this as classification. Okay, that's the terminology. You can think the simplest version is yes or no. Does it contain a cat? Yes or no. Binary classification. You could also have a bunch of different classes. Is it a car, a plane, a truck? What model of car is it? Those are classifications. They're enumerated sets. The other thing, which you're probably familiar with from calculus, and we'll talk a little bit about today, is when y is continuous. And this is called regression. Okay, right? So this is an example of something that's discrete, this cat. And the house price, this is going to be an example of regression. And that's what we're going to look at today. In lecture 3, we switch and we start to look at classification, which has some subtle differences. Okay, awesome. All right, let's look at some data. Any questions about the setup or kind of higher level questions about what it is? What goes on here? All right, sounds good. Okay, so let's look at some real data here. I'll try and get it all on the screen. So I'm going to look at this house price data. As I mentioned, this is the Ames data set, which follows a very famous data set just for historical reasons of Boston house prices that you can go look at and download. You can download it in one line into pandas if you want. Happy to put information online about how to do that. This is real data of real houses in Ames. And so what I'm showing here is like these are their row IDs. I just randomly selected some to kind of make the picture pretty, right? Just be honest. And then here's their sale price. right? So this is their actual sale price in the data, and this is their lot area. This is kind of like some notion of square feet that's actually present. This data set, I think, has something like 93 columns inside of it. I've just selected a small set of them. We'll come back to that in a second. Okay. Now, one of the things that I did here is like the first thing you should do when you're encountering a new set of data, and I cannot emphasize this enough, is look at it. The number of times that like people, especially engineers in industry, like take their data and like start running fancy stuff on it, I'm like, well, did you look? I still remember when I was running a machine learning team at an unnamed large company, and they were like, why are you sitting in the cafe just like labeling data? I was just like looking at data sets for like days. I was like, I don't know what's going on. I want to figure out what people are actually doing on this data set. And it's really important, okay? So when you're doing your projects, like first plot it. So here's a plot, right? X-axis, square feet, Y-axis, price. And clearly there's some like general upward trajectory trend here. We're going to be more precise about that in the next slide. You get bigger houses, they cost more. Maybe as you can think about it, you're like, well, that's not quite true. Like if it's in a really desirable neighborhood, it costs more, and if it's in a less desirable neighborhood, maybe it costs less. So there are clearly other factors. Those are going to be called features in a minute. But this is our first model. Okay? So let's look at one other feature. So we can also look at the number of bedrooms, right? So you see here a plot. These are categorical values. That's why I put them in there. I mean, they're kind of continuous in some way. You can still treat them as numbers, so that's fine. And you see there's some spread, among 3 bedrooms and among 4 bedrooms. And the price is the y-axis, right? Okay, awesome, right? So what do we want here? Going back up for a second, what do we want actually? We want to get a function. What's our hypothesis go from? It goes from lot area, and it predicts price. Okay, that's just notation. Okay, this is what we're after. Okay, so you show me this data, and my goal is to produce some age. Okay, now as I talked about, there are lots of functions that could take in lot areas and return sale prices. It could scramble it, it could do whatever it wanted, it could go look up from an oracle, whatever it wanted to do. There are tons and tons of functions. We're going to look at a simple restricted class of functions in just a second. Okay? But I just want to put that in your head. Like this is actually a pretty hard problem. So we need some representation for age. Okay? So how do we represent that age? Now we're going to look at a class of models which is called linear, although if you're a stickler, you'll realize right away that they're affine. I'll explain why I allow myself to cheat like that in a second. Okay, so here's a model that we could use. Okay, x1. Okay, so the idea here is you give me the variable, right, x1, which in this case would be like the square footage of whatever you have, and then I will multiply it by some theta, and this theta is going to be a weight, we'll call it, or a parameter of the model, and this is how I'm going to form my regression. Okay, looks like a line. All right, so far so good. All right. Now, let me see if I can show you a line. There's a line that does it. Okay, that's basically that line through the data that we just looked at. Okay. Now, I want to actually come one more second. How does this actually map onto this? Oops, scroll down. Sorry for the bad scrolling. Here I'm going to go to 0. Remember, my h is going to look like x equals theta 0 plus theta 1, x1. Well, what does it look like, just so you make sure the picture is clear? This here is theta 0. Right? It's where I am, it's the response at 0. And then this gives me the slope, right? This is the of slope theta 1. Okay? And then when I go to predict, what do? I grab a point. Let's grab this one. I project its value onto the x, and this is where I predict its price would be. Right? This is the price of this one. Does that make sense? Okay? All right, awesome. Okay, so this looks like a relatively simple model, but if you look at it, like, at this scale, not so bad, honestly. Right? There's some kind of linear trend there. There's some errors, or what we'll call residuals in a second. We'll try and minimize these errors. But this is like our first predictive model. Okay? And as I said, it's something that you're hopefully quite familiar with, just in kind of fancier notation for the moment. All right, awesome. Okay, so now I'm going to go, sorry for the skipping, I'm going to go and say, okay, how do we generalize this? Right? So imagine we had our data set. We had x1, x2, so on. And we have a bunch of features. And I'm going to use my features from my notes, but hopefully this doesn't cause you any panic. I have size, I have bedroom, I have lot size. And as I mentioned, in the actual real data set, there's like 80, 90 of these things, and I have price. Okay? And remember, price is my target. This is my y. And these are my x's. So this is I'm just going to put numbers here. Don't worry about them. I don't know why I wrote these in my notes, but these are the ones I used, just for the sake of consistency. So I'll write these. 45K, 30K, 400, 900. Doesn't matter too much. Okay? The thing that I care about is that this is my notation for the first data point and the second data point, and this is x11, this is x12. This is the second feature. Okay? All right. Now, I called this a linear model, right? But if you're a stickler and you took a bunch of things, you're like, no, it's an affine model. You have this, theta 0 hanging out there. The way that we get around that is we're going to assume that theta 0 for every model, x0 for every model is identically 1. Okay? So that's just a convention. Don't stub your toe on it. That is, xi 0 equals 1. And I claim, and you should convince yourself for 1 second, that means that what is linear in this new set of features is my old affine models, right? And I'm just putting a 1 here, every place. Okay? All right, that allows me to just simplify my notation. Okay? So what's the model, the class of models that I'm looking at here? Well, they're linear models again with that terminology, and they're going to look at theta 0 times x0, which we know is 1, plus theta 1 times x1 plus ... theta, and I'm going to call it d times xd. Okay? And this equals sum j goes from 0 to d, theta j times xj. All right? And remember, I'm just going to write it again, x0 equals 1. And NB means, note well, 1. Okay? All right? Now, this allows me now I have a very high dimensional problem. Now, high dimensions don't work like low dimensions. I won't go into a whole thing about it. But high dimensions are very fun and interesting spaces. Okay? You can build really interesting machine learning models by taking your data, doing what's called embedding it, and then training a linear model on top. And that actually, in some areas, is actually state of the art of what we know how to do. So those models have potentially hundreds of features that are underneath the covers. For us, these features right now are going to be all human interpretable. They're going to come from the table. So when you give me the row x1, I fill in this value here with 2104. I fill in this, the x2 value and so on, and as I go. Okay, so I just fill in the values as I go. That's how I form my prediction. Okay, a little bit more notation. All right, now if you don't remember, I'm just going to introduce vector notation here. These are column vectors. They're going to look like this, and this is just going to save me time and space and fill with things. D. Okay, x1 is going to be a vector 2. With x11, x2, x12, so on. Oop, sorry. Sorry about that. I wanted to start at 0. x10, x11, and so on. And remember, this thing is 1, as we've said many times, and this is whatever the value is up there, 2104. Okay? In general, this is going to be the size feature, the bedrooms feature, and so on. Clear enough? Right? These are the parameters, and these are the features. All right, so why be so pedantic about this piece? It's because we're going to use this in several different guises. These parameters are going to mean different things as we change the hypothesis function over time. And we just want to make sure the mapping is clear. So just make sure the mapping is super crystal clear in your head of how I take a data point that looks like this and map it into a feature vector that looks like that. That's all that I care that you get out of this. And then we have some different vectors. Okay? And yi is going to be the price in our example. Is price. Okay. Now recall this notion we didn't pick this by accident. This was a training example. This pair, xi, yi, is a training example. Right? This is the ith training example. Right? Just the ith one in the set. Okay, so far so good. Now, I'm going to create a matrix here, capital X, that's going to have one row for every example. Oops. So on, X. So there are n of those characters by my notation. And so where does this matrix live? Well, there are n rows, and recall because of my convention that I added a extra dimension, which I always made 1, it's d plus 1. And I'm just highlighting this and being pedantic because I don't want it to bite you when you realize, like, why do they have D+1? Where did it come from? It's the 1. And this is someone who's saying this, who's taught this course many times. Someone's going to get bitten by it. I'll say it many times. Okay? It's uncomfortable when it happens. Okay, so this is now I can think about my training data as a matrix. Awesome. Okay, so now we have a bunch of notation. I've basically bored you to death with 100 different ways to write down your data set, but I haven't answered the question that we actually cared about, which is, how do I find something that's good, right? How do I find an example of something that's good, all right? So now let's look at here. So why do we think this line is good? You remember this from how you fit it. You think it's good because it makes small errors, right? Like if it were all lying on the line, right on top of the line, the distance from any point to the line would be 0. And we'd think the line was pretty good if we could kind of minimize those errors, okay? And this is the error, this is the residual. Now, for computational reasons and historical reasons, we'll look at the squares of those residuals in just a second, okay? Don't worry too much about that. You can do everything I'm telling you with the absolute value of the things. Right? You don't want to do the signed value of them because what does a negative error mean? Right? You should pay a penalty, is the intuition, whenever you make an error. Okay? All right. So let's look at this. All right. So we're going to look at our h, and I'm now going to write it sub theta. J goes from 0 to d, theta j of xj. Okay? So now, picking a good model, I can actually make some sense for. What do I want? Well, I want somehow that h of theta x is approximately equal to the y when x and y are paired, right? If x and y come from a new example, you show me a new image, it has a cat or not, that label may be opaque to me, but it exists. I want my prediction to be close to that y on average. Or for house prices, you give me a new house, I predict its price as close as possible. I may not get the exact dollar, but it should be penalized a lot if I'm off by $1 million, maybe, but not if I'm off by $10, right? That's kind of the intuition here, right? So how do I write that down? The idea is I'm going to look at this function j, which we're going to come to a couple of different times. And that 1/2 is just normalization. I'm going to look at my data, and I'm going to say, take my prediction on the ith element, yi, and square it, okay? Now this is our first example of a cost function. And I wrote it in a really weird way. But I want to come back to why I'm doing it this way, okay? This is also called least squares. You've probably seen this a bunch of times, and that's okay. And if not, don't worry. We'll go through it. There's nothing mysterious, okay? So let's unpack it. So this thing here is the prediction. It says you give me at a point xi, what's my prediction on xi? Some y. And that says it should be close to whatever the training set said yi was. Remember what we're given? We're given xi and yi pairs that are together. Image, cat. House information, all of its description, and the price. We should be close, okay? We're penalized more for errors that are far away. I could give you a big song and dance about why this is appropriate, and indeed, there are lots of statistical song and dances about it, but really we're doing it because it's easy to compute everything that I'm going to do. You just want something that's kind of sensible, right? Like, you should be penalized more the more wrong your guess is, right? Roughly speaking, in this example. Okay, now, what does it mean to pick a good model? Well, our model is now determined solely by those theta j's, right? If we knew the theta j's, our model would be completely determined. That was the trick I pulled on you when I said, oh, how are we going to represent our hypothesis? We're going to represent it in this class. That means now we've reduced from all the crazy functions that you could have ever dreamed up, any computer program that you could ever have written that was functional, to the class of functions that are represented by these weights. The wild thing is, there's a lot of functions you can represent that way. Okay? And we'll see that over the course of the class, okay? Especially when you start to get really high dimensions. Okay, cool. So which one am I going to pick? Yeah, please.
So for this least square cost function, I'm understanding that for cost function, what is important to us is just the gradient. So why do we need a 1/2 constant in front?
Awesome question. Yeah, very advanced question. So the question is, hey, you wrote this 1/2 there. It seems unnecessarily and potentially confusing. Why would you pay the cost to do it? And the reason is, when I take the derivative in a minute, it will cancel out and make my life easier, okay? But there's no, and the other point that you made is, and I love the way you said it, this is exactly right. We don't care, I wouldn't call it that we care only about the gradient, but we only care about the minimizer. for the loss function. So if your loss function costs 10 or costs 100, doesn't matter. What you care about is what theta minimizes it, and you got that concept exactly right. So I hope that makes sense. When we're setting up the cost function, in some ways, sometimes we give it an interpretation almost to debug it, to understand what it's doing, but really all we care about is what is the theta. When we minimize over all the thetas of j theta, this is what we're solving for, right? So we basically want to solve this j theta. Now, as we'll see in a second, for linear functions, we can do this. For more complicated sets of functions, it's not always clear that there even exists a minimizer that we can reasonably find. Okay, right? So there could be these wild functions that take bumps and everything. So I'll draw one for you in a minute, right? When we talk about solving it. But for linear functions, what's amazing and why we teach the normal things, you can prove what h theta is in this example. Wonderful point. Okay, but that's the central thing. We're going to set up these costs so that we get a model out. We've restricted the class of what we're looking at to something that's relatively small where we can fit the parameters. Then we just have to minimize. Okay, awesome. Right? This is what I mean by optimization, by the way, is solving this equation. Okay? I haven't told you how we're going to solve it yet, but hopefully this is good. Now, just for leading a little bit ahead and also to kind of stall in case anyone wants to ask a question, what we're eventually going to do is we're going to replace this j with increasingly complicated, potentially functions that we're going to look at, one for classification, one for other statistical models. But we're going to do almost everything that comes after this part to all of those models. So once we kind of get it in this form where it's like a prediction and some penalty for how poorly it's doing, we may use different cost functions. Everything that comes next, we'll be able to do for all of them. Okay? That's why we set up all this kind of elaborate notation for like fitting a line. It is still, by the way, boggles my mind how much machine learning you can do by just fitting lines, like just higher and higher dimensional lines. But we can talk about that some other time. Okay, awesome. Okay, all right. So how are we going to solve this? Now, there are many ways to solve this. If you've taken a linear algebra course, you're like, oh, I compute the normal equations and then I'm done. Least squares, you're a MATLAB or a NumPy person, you're like, oh, I do least squares solve or whatever it is, backslash, whatever you want to do. We're going to solve it in a way that sets us up for the rest of machine learning, because machine learning will deal in functions that aren't quite as nice as linear regression quite a bit. And in fact, the trend has been, when I first got into machine learning in antiquity, we were all about what were called convex or bowl-shaped functions, just roughly, and we were really obsessed. Were we getting the right theta, right? We're like statisticians, like at large scale, can we get the right theta? Is there one individual theta? Modern machine learning doesn't care. We don't even know if we get the right answer. We don't even know how. There's a paper I was reading from DeepMind this morning that was like, oh, you should run your models longer. No one noticed. Right? How do we not know when to run the models longer? We don't. That's the world we live in. So how does this work? So imagine we want to, this is our cost function. Okay? Now, just as an aside, I want to say the linear function doesn't look like that. So don't think about it. The linear function looks nice and bowl-shaped. Okay? The reason that's important, as I was just saying, is a local minimum, this is a local minimum, so is this, roughly speaking, is global when you're convex. If that doesn't make sense to you, don't worry about it. Okay? For convex. We'll come back to that point later in the course. But I just want to say, don't think of this function I'm drawing here as what happens with least squares. We're just optimizing a j for right now. Okay? All right, so how are we going to do it? We're going to use a very simple algorithm. We're going to start with a guess, which is going to be theta 0. How did we pick this guess? Felt good. Randomly. Set it to 0. All reasonable things to do. There are entire machine learning papers, by the way, written. I've even written some, which I'm not sure if I should be embarrassed or proud of, that talk about how you initialize various different parts of the model. Okay? For us, though, it won't matter for least squares and some of the other models we're studying because we'll be able to get to the right solution. Okay? All right, so now imagine, for the moment, I found you a model. I found you an initial model. Well, it's clearly, from looking around, imagine I'm the point and I'm looking, clearly I can go down from here, right? So the natural greedy heuristic is compute the gradient. What does a gradient look like here? It looks like this. Oops, I can do this fancier. Okay, can you see that? Good. I compute the gradient, and then I walk downhill. Sound good? Right? Tells me to go downhill from here. Right? Whatever shape I'm at, this gradient will also tell me what to do. Now there's some problems, right? Just as an aside, what if I were right here? Ooh, it doesn't tell me what to do. But don't worry about that. It's a local maximum. I'd be toast. But here, tells me to go downhill. Okay? Now once I go downhill, how far do I go? Again, feels good. I pick a value. It's called a step size. So my next value is going to look like this. T plus 1 is going to be defined to be 5t minus some alpha theta j theta t. Now my notation is a little bit weird here. Imagine it's one-dimensional for the second. Okay? Compute the gradient, go in the opposite direction. Okay? That's all that's going on. This thing here is called a learning rate. Embarrassingly, I think I have won awards for papers that are about learning rates. But they are not very well set. So you just kind of pick a value. For deep learning, people now have all kinds of what they call adaptive optimizers. If you look in the literature about how to set these values for you, you don't want to set it too big or too small. There is a theory about how to do it for linear things, but don't worry. For you just kind of pick a value, okay? Just imagine like what could go wrong. What happens if you pick it too big? Well, then you kind of shoot off over here, right? You pick it too small, then you make little bumps like this, right? You don't make enough progress. It's not too hard to think about what should happen here. And then what happens? Well, I get a new point. This is my theta 1. And as suggestively done here, I iterate. I compute the gradient and I bounce down, and then hopefully I get closer. Please.
What's the denominator?
Oh, sorry. That is just this is my notation for the gradient with respect to theta. This is a partial derivative with respect to theta. Right? So imagine it's one-dimensional, and I'm just setting up for the fact that I'm going to use multiple dimensions. It's literally just the gradient with respect to theta. Cool. Yeah. The derivative in this case. Okay. Now what I'll do is I'll compute that j for all 0 to d characters, and that gives me my high-dimensional rule. Okay. Please.
Is this j only for one data point?
Yeah, so right now I've just shown j as an abstract function. I haven't decomposed it as a sum. That's a great point. Let's come back to that in 1 minute. Exactly what happens when we have a data point. It's going to be my next line. Awesome. Other questions? Okay, is it clear? So I did actually a fair amount of work there and tricked you, just so you're clear. I went from 1 dimension to d plus 1 dimensions by just changing the subindex and did them all by themselves. So make sure that sits okay with you, right? Please.
How can we understand the gradient of this thing on graph?
Yeah, so how can we understand it on a graph? What do you mean by on a graph? Like on this graph in particular?
Yes.
Awesome, yeah. So just imagine that, so the one-dimensional case carries what you need to deal with. So you're in a particular basis, right? Meaning you have like theta 1, theta 2. So imagine I'm standing in two-dimensional space. I can look down one axis and then I have a one-dimensional function. Then I have a gradient there. That gives me the vector in this direction. Then imagine I turn 90 degrees orthogonally. I look 90 degrees there. I get another one-dimensional function. I compute its gradient. Now the gradient is actually, if you look at the derivative, it's actually all those vectors put together, one after the other in component. But that's exactly right, yeah. So yeah, but you're asking exactly the right questions. Right? So just picture it as the tangent to the curve if that helps you in high dimensions. If not, don't. Yeah. Cool. Wonderful questions. Okay, so what do I hope that you understand? Here's some rule. You have the intuition that what it's going to do is it's going to bounce slowly downhill, okay? Now, if you start to think about high dimensions, and I think this is why the question came, it starts to get a little weird. What does it mean in high dimensions? You can imagine like something that looks like a saddle, if you know like a saddle, and you're like, oh gosh, what's going to happen when I get to the top of the saddle? Clearly I can go off the sides and get a little bit smaller, right? That would be good. Maybe it goes down and stops, but I could get stuck on the top of the saddle too. And weirdly enough, it's called the saddle point. Don't worry. Okay, sound good? Right? We're not worrying about convergence, right? Notice this algorithm has a very clear error mode. Here, we found what looks like the global minimum. But what if we started here? We would go bounce, 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 and we'd find this one. Now, how do you stop this algorithm? You stop the algorithm when this update becomes too small, okay? And you set that tolerance. Maybe you set it to what's called the machine precision, like 10 to the minus 6, 16. Or you set it to 10 to the minus 8. Or you want a quick solution, 10 to the minus 3 or something. But the point is no matter what you do, you're going to get stuck here with a descent method, because it's going to go downhill and get stuck here, and you're going to miss this much better solution. That won't happen for linear regression. We won't talk about why at this exact moment. We can prove it in a little bit. But for things that are bowl-shaped, every local minimum is a global minimum, and then we're in good shape. That's why we cared so much about these things 10, 12 years ago. We care about them, occasionally now. Less than we used to. Okay. All right, so let's compute some of those derivatives, getting back to the earlier asked question, which was, hey, what does this mean for a sum? Okay. All right, so remember Rj had a very particular form. So we're going to compute the partial derivative with respect to some sub j of j theta. Okay, so this is the derivative here, oops, the derivative with respect to the jth component. Okay, now, we take the sum, I goes from 1 to n. I'm going to put the 1/2 inside because I can. And then this is linear. I'm going to come back to what that means in 1 second. Okay, I just did a little bit of work here, not much. I just rewrote the definition of j, which is this sum. And then I took the partial derivative and I pushed it inside because it's linear. Okay? And we should know that gradients are linear. Okay? Now, when I do that, I get something actually fairly intuitive. And this makes my heart sing. Times partial derivative theta j h theta of x. Okay? Now, this is I canceled the 2 with the 1/2, back to the question about kind of the cooking show preparation. And that is standard, by the way. Now, look what I have here, which is kind of nice. This thing is basically the error, but it's signed. It tells me which way I'm making a mistake. Kind of too high or too low, right? That's all that thing is. This is the misprediction, or the error. Okay? Now I have the derivative with respect to the underlying function class. Now, why did I bother to write it out this way? Clearly, I could have skipped the step of doing this and jumped right to the end, but this is going to be general for almost all the models we care about. That's why I did this. Okay? So what is it in this specific situation? Well, recall h of theta of x was equal to theta 0, x0, plus theta 1, x1, plus theta 2, x2, plus computing the derivative of this is pretty easy. It's just, theta j, h theta of x is xj. Right? Please.
The second line, why do you have no superscript over x on the right?
Superscript over x on the right.
On the second line. Where you're put up
Here?
on the right. Right to left.
On the right here?
Yes.
Oh, this should have a superscript. Oh, I'm so sorry. Great catch. This is at that data point. Yeah. Wonderful catch. Thank you.
So I was saying generalizable because your h theta could be like a polynomial equation or some trigonometric.
Could be whatever you want. All I care about is this is the error times the derivative with respect to that underlying model. This is a very basic version of like what looks like a chain kind of rule, and we're going to use that like nobody's business. So if you didn't know the chain rule before this class, you will definitely know it by the end because we use it nonstop. But yeah, this is just set up for that. That's why it's generalizable. It's the error, which is totally generalizable for any model that has to do with prediction, times how you compute the derivative, like what's the change of the underlying model. We'll be able to generalize that. And in this case, it's just xj. Right? So now, right, getting back to this, what is our whole rule? It looks like this. Theta j, t minus alpha, sum over all the data, answering the earlier question. At this point, we're doing what's called batch gradient, which we'll come back to in 1 second, minus yi times xij. Now notice, I'm going to try and do some highlighting here. I hope this is okay for people to see, and I apologize if you're colorblind and this doesn't help you too much. But these are the same. Okay, hopefully these are distinguishable colors, these J's. And then the I's are the other index that's going on, and these are the data points themselves. Okay? So I look at every data point, and I'm doing the jth component of each one. Right? Now, by the magic of vector notation, here's what I can do. I just write this as this. H theta, xi, this doesn't change. This is a vector equation. Okay? Okay? So this is basically looping over all the j indices at once. Okay? If you're unfamiliar with vector notations, one of the reasons I'm doing this quickly is I will do it secondhand throughout the course. It's not deep. It's not like it requires a lot of stuff. It just requires a little bit of reps. Kind of repeat on them, please.
So about the learning rate alpha, do we have to use the same rate for every theta, or we can use different alphas?
Wonderful question. So alpha you will typically set for an iteration, right? When you take a step. You can change it across steps. So one thing is, here I've said alpha does not depend on t, the iteration step, but in general it usually does. You usually decay the learning rate over time. So that's just what's done in practice, and that's done for really good things. What you don't typically do is have alpha depend on the data points itself, because then it's kind of almost functioning like a free parameter, at least in classical machine learning. But in both optimizers, one of which was invented by our own John Ducci and other folks, you actually do change the alphas for every different coordinate, which was, I think his first paper was at a grad and then at a delta. So people do things like that are a little bit more sophisticated, and why they do those, I'm happy to explain offline. But right now, just think of alpha as a constant, like it's small enough that it's not gonna lead you too far astray. Like if it were too big, you'd jump too far, and maybe you could do a little bit better, but maybe not too much. In fact, this very basic rule, which is called gradient descent rule, is actually very widely used. Very, very widely used, with just one alpha. Wonderful question. And those are the right questions to ask, like, how does this parameter depend on what's around it? Start thinking like that as you go through the course. That's really, really helpful to understand. Okay, so far so good. So at this point, we know how to fit a line, which doesn't feel like a huge accomplishment maybe, but I think it's pretty cool. And we fit it in this kind of obfuscated general way that's gonna allow us to do more models, I claim, but I'll verify that in 2 classes. This vector equation here is just showing you like all the things that we computed. This is specific, to the earlier point, to the line, right? This gradient here is this guy. Those are the same. That's why this model popped out, okay? Awesome, and we'll come back to that in a minute. Okay, now, a topic that is practically quite important for machine learning is, and was hinted at earlier, is, and I'll copy this equation, is what do we do in practice? So one thing that we may not like about this equation is this thing is huge. In modern machine learning, we'll often look at data sets that have millions or billions of points, right? Well, it's not uncommon to run models where you're like, every sentence that has been emitted on the web in the last 10 years is a training example, or every token, right? Every word. And it would be just enormous, right, at that point. It'd just be a huge thing. So even doing one pass over your data is potentially too much, okay? Now that's a really extreme and crazy version of that. But you can also imagine situations where you're looking at hundreds or thousands of images and you potentially want to look at fewer. So we'll come to how we do that in a second. Sorry, yeah?
Superscript above the first data set?
Oh, it's t and t plus 1. These are the steps. Remember we started at theta 0, so superscript 0 was our initial guess here. And then we moved from 1 to 2 to 3 to 4. And so this is just the recursive rule that takes you from theta t to theta t plus 1.
So theta t is just whatever current data we're on.
Exactly. So you just imagine it as it's a kind of recursive way to specify we're at particular t, and here's how we evolve to t plus 1. Exactly right. You got it perfectly.
T is a vector for the data.
Exactly right. So theta t, when we go back to here, oops, sorry, I hope that's not dizzying. I wish there were a way to skip without making you sick, is this vector. It's just a particular instantiation of those vectors, one for every of the d plus 1 components. Yeah, please.
These steps are completed.
Yeah, so we will take steps, as I said, until we converge, typically, or we can take a fixed number of steps. I'm eliding that because for this particular problem, I can kind of give you a rule of thumb. I can point you out a paper that tells you how to set alpha. In general, for machine learning, as I was kind of very obliquely referring to, we don't actually know how to tell that we've converged. And part of the reason is, if you knew your model was this nice bowl-shaped, then you can actually prove that the closer you get to the optimum, the smaller your gradient is getting, and you can predict kind of how far away you're going to be, basic for a nice class of functions. For nastier functions and the ones that we're going to care about more, you can't do that, so it doesn't make sense to say that you found the right answer. And so I don't emphasize that. For these models, I can give you a beautiful story, happy to type it up online and tell you, but in general for machine learning, honestly, we just like run it till it feels good. Like, oh, the curve stopped, it stopped getting better. And that was this DeepMind paper that said, hey, for these really large 280 billion parameter models, so their theta has 280 billion parameters in it, They're like, we didn't run it long enough. If we kept running it, it was better. And like everyone who works in machine learning for long enough in the last 5 years has a situation where they forgot they were training a model. Hopefully, like you're not paying for it on AWS or GCP or something. And then you come back like a week later and it's doing better than you thought. And that is a very strange situation. So I don't have a great rule for this. For your projects, it will be clearer. I'm telling you the real stuff though. Yeah, awesome, please.
This equation is the plus one minus
So we will only use it in the forward direction of going t to t plus 1, but you could imagine that it's reversible if you want it. Oh, wonderful question. Yeah. So in the sense that like if you shoot past, let's go back here. So if you're here and you shoot past, your step is kind of too big for the gradient, you kind of trust it too much, then in the next iteration, the gradient will point in this direction, right? And so you'll step back. So it will actually have kind of this ping pong. And that's actually, you actually want that to happen. It turns out the optimal rate, I mean, I can bore you with this for days, the optimal rate is actually when you're doing that skipping for whatever reason. Yeah, but it's more intuitive for people to roll down the hill. Yeah, wonderful point. You got it exactly right. Please.
So is it possible for the update to be 0, even if h theta of xi is not necessarily y or 3i?
Yeah, so it's not possible for it to be exactly 0 everywhere, but it's possible to have gradients that are not giving you any information. Yeah, wonderful question. Absolutely wonderful question. It's because it's a linear system, right? So it's not full reg for the linear algebra nerds. Yeah, wonderful question. Please.
So let's say you have like this function or something, right? But you flip it, so theta 0 is equal to 0, but on the other side, when you only get the local minimum over there and not the actual like...
Exactly right. Yeah, and that's what I'm saying. Like, we used to worry about that quite a bit. Now we just say it's good. I wish I could tell you something better than that, but we'll get into why that's true. But yeah, when your function is in a good class, and good here formally means like convex and bounded in some way, then you will provably get to the right solution. We'll talk about those conditions later. The reason I de-emphasize them now is because modern machine learning actually works on functions that look like this, not on the other class of functions. And so that's less important for students. And then you would rightly say, like, you told me all this stuff, I memorized all these conditions, and then I got into the workforce and like none of them worked and no one uses them. Like, yeah, that's true. But you're exactly right. And so people worry about initialization. Where do you start so that you are kind of guaranteed to get a good model? In fact, there were a couple of awesome theory results, I think one from my group, one from Tengyu's, that said for certain class of these nasty non-convex models, if you initialized in a particular way, you would be guaranteed to get the right answer. Actually, I'll show you one in week 11, a simple version of that, where if you initialize cleverly, there's not a unique answer, but you'll get the right one every time. Yeah. Or sorry, class 11, not week 11. Yeah. Yeah, people try random initialization. The problem is the trend is for models to be really expensive. So you run huge models. So any one run could cost a couple $1 million. Like I was looking at the Amazon's GPT-3 service. I think it costs like $6 million a month to run. So like, do you want to try to run it multiple times? Like if you got money, go ahead. But you kind of want to try and do other tricks. People used to do a lot more random restarting. Now we've kind of, it's really sad to say this is the state, but we've kind of evolved like folksonomies. Like if you train these models, you kind of know, what are the right parameters and what is everybody else using. And not everyone tries and explores everything, let alone how long you tune it, what optimizers you use. We kind of all use the same stuff, but we don't have great formal justification for it. Maybe I'm exposing too much. It's not as bad as it sounds. There actually are principles in this area. I'm just like telling you the plates that are broken because they're more interesting to me. Yeah. Oh, wonderful question. We're going to come back to that. So the solution is like, there's a phenomenon that a lot of people know about in machine learning, which is if I take my model and I exactly fit my training data, maybe it won't generalize well. Like it'll fit to some error, some noise in the data, and this is roughly overfitting. We cover that in lecture 10. In lecture 10, at least when I taught it last, I also taught about something which is in modern machine learning. We realized that actually sometimes that concern is overstated for some models. And there's a wonderful paper by Misha Belkin that said you can actually interpolate, perfectly fit your data and optimally generalize for some classes of models. So that trade-off isn't as clear for modern models as it was for old models. Maybe I should stop telling you about this stuff. But yes, in general, overfitting is a problem. You can overfit a model and believe your training data too much. Yeah, but this area is fascinating. I can obviously rant about it for weeks. So. Wonderful questions. Yeah, this is absolutely great. Okay, so what do I want to tell you? So I don't want to tell you normal equations. I thought that was pretty clear from the beginning. So you can read about those. If you want, I'll type up notes. Andrew's notes are great on this point. But I do want to tell you this one little bit with my last couple of minutes about batch versus stochastic mini batch, because it actually is relevant and useful. Okay, so when we last left off, we were looking at this equation, and we noticed this problem that n was really big. And I just hopefully told you, like, n is really big, and so is d. The number of parameters is really big. So this is expensive. I wouldn't want to look at all of my training data before I took my first step, because probably my initial guess is not that good. That's why I'm training a model. Like, if randomly initializing the model, which is something people try to do, gave me good predictions, I just use that. So obviously I want to take as many steps as I can. So here's what I'll do. I'll use mini batches. So what does mini batching do? Okay. I won't get too formal, but basically what I'll do is I'll select some b, let's say at random. Okay, I'm being vague here what random means. I wrote a bunch of papers about this. You can either pick, randomly select them, or you can shuffle the order. And in conventional machine learning, we shuffle the order for a variety of reasons. And then I pick b items. So b is going to be much smaller than n. Okay? All right? And then I update I'm going to call it this, because this made it more clear. I equals 1 to n. Or actually, I'm going to write it a little bit strangely. I apologize for this notation. The notation's better in my notes, but I want to write it this way because it's easier to say. xi, yi. It makes it more clear what's going on, I hope. Okay, what's going on? So I select a bunch of indexes b, and then I just compute my estimate of the gradient over them. Okay? I could even pick b to be size 1. Just pick a single point, as someone was alluding to earlier, and take a step. Now, what are the obvious trade-offs here? On one hand, if I pick a step, that step is really fast, right? If I pick a single element, it's super fast to compute relative to looking at the entire data set, but it's going to be noisy. It's going to have low quality. I may not have enough information to step in the direction I want to go. On the other hand, if I look at the whole data set, it's going to be super accurate about what the gradient is. In fact, I'll compute it exactly up to numerical issues. But it's super slow. Now, what people do is they tend to pick batches that are on the smaller side, right? And you pick them kind of as big as you can tolerate. And I won't go into the reasons for this underlying hardware. Happy to answer questions about it. But basically, you pick batches that are kind of as many as you can get for free. Modern hardware works kind of in parallel. So you'll grab and look at like 128 examples is not much more expensive than looking at one. Okay, on a modern kind of platform. Now, I'm using these noisy kinds of proxies, and you may think, am I still guaranteed to converge? And the answer is effectively yes, and under really, really harsh conditions. In fact, I'm very proud of something that my first PhD student and collaborators, Ben Recht and Steve Wright, wrote about. This paper called Hog Wild, which is very stupid, has an exclamation point, but also got a 10-year Test of Time award for saying that you can basically run these things in the craziest possible ways, and they still converge, these kind of stochastic sampling regimes. Okay? I won't go into details about that. My point is, like, this thing is actually fairly robust. This kind of take a bunch of error estimates and step them. And in fact, almost all modern machine learning is geared towards what's called mini batching. If you download PyTorch or JAX or TensorFlow or whatever you're using, odds are it has native support to give you mini batches. Okay? And that is basically just taking an estimate of this piece here and using that noisy estimate. And why might that make sense? Well, imagine your data set contains a bunch of near copies. If your data set contained all copies, then you would just be reading the same example and getting no information, right? If instead you were sampling that same example, you would go, potentially unboundedly faster. And if you think about like what we're looking at, when I told you images, like the images on my phone for my daughter, there are a lot of pictures of my daughters, a lot, okay? I'm a regular dad. I take lots of pictures. So that means there's a lot of density. And so machine learning operates in these regimes where you have huge, dense, repeated amounts of data, okay? All right. So this is going to come back. We're going to see this next time. We're going to see it in particular when we start to look at various different loss functions. We're going to generalize how we do prediction to classification next time, and then to a huge class of statistical models called exponential family models. To go back to the top, I skipped, just to make sure you know what's here and what I skipped, we went through the basic definitions. We saw how to fit a line. We went through batch and stochastic gradient descent of how to solve the underlying model. We set up a bunch of notation. This is going to be one of the drier classes where I'm just like writing out all the bits of notation. And we saw how to solve them. Those will all carry over to our next brand of models. The normal equations, if you run into problems, blame me. I'm happy to take a look through them. They're relatively straightforward, and the notes are pretty good, but I'll look at Ed if you run into any problems there, and happy to answer questions. With that, thank you so much for your time and attention, and I hope to see some of you on Monday.